At the end of this video, you should be able to examine the motion of a fluid using the continuity equation and recognize the effects of Bernoulli's principle on fluid motion. Fluid flow. Some parts of a river flow smoothly. At other places in the river, there may be foamy whitewater rapids. The smooth stretches of a river are regions of laminar flow. Every particle that passes a particular point moves along the same smooth path traveled by the particles that passed that point earlier. The foamy rapids in the river are regions of turbulent flow. The flow of the fluid becomes irregular above certain velocities or where there are obstacles or sharp turns. Irregular motions of the fluid, called eddy currents, are characteristic of turbulent flow. The ideal fluid model simplifies fluid flow analysis. Many features of fluid motion can be understood by considering the behavior of an ideal fluid. An ideal fluid is a fluid that has no internal friction or viscosity and is incompressible. A fluid is incompressible if the density of the fluid always remains constant. Although no ideal fluid exists, the ideal fluid model is a useful tool for understanding the properties of real fluids. The term viscosity refers to the amount of internal friction within a fluid. The more viscous a fluid is, the slower it flows. Ideal fluids are considered non-viscous. Ideal fluids are also characterized by a steady flow. In other words, the velocity, density, and pressure at each point in the fluid are constant. Ideal flow of an ideal fluid is also non-turbulent, which means that there are no eddy currents in the moving fluid.
In physics, we often make approximations and simplifications. For instance, we might pretend that a collision is perfectly elastic or that a surface has zero friction. Similarly, we can pretend that a fluid behaves as an ideal fluid. Ideal fluids are incompressible, meaning that they retain the same volume under pressure. Ideal fluids also have zero viscosity, meaning they have no internal friction. One way in which viscosity manifests itself is in the resistance of fluids to flowing through pipes. Finally, ideal fluids exhibit non-turbulent flow, meaning that no eddy currents form in the flowing fluid. Real fluids never completely reach the standards for an ideal fluid. However, many fluids can be approximated as ideal fluids for slow flow speeds at low pressures or inside smooth pipes.
Principles of fluid flow. Basic physical laws lead to some principles of fluid flow. The continuity equation results from mass conservation. The diameter of the pipe shown on the side and bottom column right now is different at each end. The mass flowing into the bottom of the pipe, which we'll call m sub 1, must equal the mass flowing out of the top of the pipe, m2, during any time interval. So m1 must equal m2. Mass is also the product of density and volume, so we can say m is equal to rho v. Because m1 is equal to m2, we can substitute rho v in for each mass. So we have rho 1 times v1 is equal to rho 2 times v2. The volume of a cylinder is v, and it equals the area times delta x, where delta x is the length of the cylinder. So we can now substitute in rho 1 multiplied by the area of 1 multiplied by the length of 1 is also going to be equal to rho 2, or density 2, multiplied by the area of 2 multiplied by the length of 2. The length of the cylinder, which is delta x, is also the distance the fluid travels, which is equal to the speed of flow multiplied by the time interval. Remember, delta x is equal to velocity times delta t. The time interval and the density are the same on each side of the equation, and therefore cancel out. And so the resulting equation is known as the continuity equation, shown at the bottom of your screen here. The speed of fluid flow depends on cross-sectional area. The product, AV, or area times AV, which has the units of volume per unit time, is called the flow rate. The flow rate is constant throughout the pipe. So the fluid speed is faster where the pipe is narrow and slower where the pipe is wide. The pressure the pressure in a fluid is related to the speed of flow. On the image on the screen here, the image shows a waterlogged leaf in a drainage pipe. The water and the leaf move faster through the narrow part of the tube than through the wider part of the tube. The water and the leaf are accelerating, so an unbalanced force acts upon them. This unbalanced force occurs because the water pressure in front of the leaf is less than the water pressure behind the leaf. The pressure difference causes the leaf and the water around it to accelerate as it enters the narrow part of the tube. This behavior illustrates Bernoulli's principle. The pressure in a fluid decreases as the fluid's velocity increases. The lift on an airplane wing can be explained, in part, with Bernoulli's principle. Air flowing above a wing moves faster than air below. The pressure above is less than that of below, and this produces a net upward force on the wing, also known as lift.
Bernoulli's law relates the pressure in a fluid to the speed of the fluid flow. Here you can see that water from a wide pipe must speed up when it enters a narrow section of pipe, because the same volume of water must flow through a smaller area in the same amount of time. If a leaf were flowing along inside the pipe, the leaf would speed up along with the water that carries it. Newton's law reminds us that some force is required to explain the acceleration of the leaf. Because the acceleration of the leaf is to the right, the net force must also be to the right. It must be that there is a higher pressure where the pipe is wide and a lower pressure where the pipe is narrow. This pressure difference results in a net force to the right, causing the leaf to accelerate. A pair of pressure gauges connected to the pipe confirms our thinking. The pressure in the wide pipe is greater than the pressure in the narrow pipe. Bernoulli's principle says that the pressure in a fluid decreases as the fluid's velocity increases.
At this point, you should be able to satisfy the two objectives listed at the beginning of this video.